Thanks, Vishnu, for this nice introduction. To say the title, which I don't dare to speak that word. I would like to thank Raj for inviting me here, and for you all to be here. And it's a great pleasure to be in India. It's my first time. I'm very positively impressed. It's how warm and nice are the people, and also the science. Okay. So what I have for today. Since there are many students, I'll start with a brief introduction of what is condensed matter physics and why I study it. And then I move on to some basic concepts in phase transitions and try to do a historical overview of the disorder effects in this matter. There is a disclaimer here because I'm not going to do a thorough review on the historic facts that happen. It's a lot, so I chose just a few ones, but I hope it will give you some flavor of how concepts have evolved since the late 60s, 70s. And then I will go to do a little bit of technicalities here, which usually we shouldn't do in a colloquium. But I'm a disorder guy, so I will go against the wave. And I will talk about this the strong disorder normalization group. But I hope the technicalities doesn't put you to sleep. And why I'm doing this, I want to show how the Indians are culprit in this field, because this method was exactly invented by some colleagues of you. Okay. And please interrupt me anytime that you want. So our story can start. There's many ways of telling this story, but I'll start with Pauli, where he said that solid-state physics is dirty physics, and one shouldn't wallow in dirty. And same thing for Gelman, that he was saying that solid-state physics is quality-state physics instead of solid-state physics. So there was a lot of mockery on solid-state physics and condensed matter physics in the early days, simply because people thought that physics should not meddle with these dirty things that it has in nature. We should just do beautiful equations and mathematics. Although Pauli have somewhat invented, he claims to have invented condensed matter physics because in the early days he did Pauli paramagnetism. But seems that he was trying to deny it somehow. Okay, so traditionally condensed matter physics was called solid-state physics, and it was the physics of solids and liquids. People were more interested in structure of crystals. The X-ray was just invented. Melting and evaporation, just simple. Not simple as for today, in the sense that we were just inquiring the first basic questions, and these science, these part of physics was just getting born. Today, this field has evolved, and we now classify this field as studying the complex X. What do I mean by that? For instance, high energy people study the X of length, very short length scales, or very high energy scales. Cosmologists study the scales of very large structures of the universe. So which scale studies condensed matter physics is the scale of complexity. So we study more and more complex systems. And this has to do with the evolution of this field in the sense that we now understand how matter assemble itself at lower and lower energy scales, and how they undergo phase transitions, lose symmetry, and becomes more complex. Another way of why to bother in dirty physics is because of technology. Mainly all technology that we have nowadays are due to condensed matter physics. So each bullet point in this slide is a Nobel Prize. The invention of transistors, semiconductor integrated circuits, magnetic recording devices that we love so much in our cell phones, liquid crystals for everything practically. Well, that clock is not using liquid crystal, but okay. There is no here, okay. But there is in your cell phone as well. Superconductors, LEDs, graphene, quasicrystals, and so on. Even for metrology, condensed matter is important. Now we define the length of units, and the kilogram uses the quantum Hall effect to calibrate what is a kilogram. And from the fundamental point of view, if you wish to still do beautiful physics, there is beautiful physics in condensed matter physics. This beautiful physics comes with a mot word behind it, or you could say a philosophy behind it, that more is different, which is coined by Phil Anderson in the early 70s. So in the following sense, when you put many parts, individual parts, interacting together, new phenomena may appear. And these new phenomena are so complex that the basic rules that govern each individual component becomes, in practical sense, irrelevant to describe the system. So for instance, if you want to describe a liquid, we just need Navier-Stokes, which then we need to characterize the fluid by its compressibility, density, and viscosity. But I don't need to know anything about the atom to describe the liquid. So all the physics that govern the atom becomes irrelevant, and we have to describe the fluid, we need the Navier-Stokes, not Maxwell equation. And the same thing for the atom. We do not need to know chromodynamics to understand the spectral lines of an atom. Given that chromodynamics govern the quarks inside the nuclei, once you undergo a phase transition, meaning that you cool down it and the quarks confined, then you have a new emergent structure, which is the proton. And with the proton interacting with the electron, then you describe all the spectral lines. But you don't need chromodynamics for that. So that's more or less the philosophy of dirty physics or condensed matter physics, that in sum, for understanding the universe, theory of everything is necessary but not sufficient. If that was not the case, then we could apply the reductionism of the old Greeks, like saying that, well, sociology is just applied physiology, and physiology is just applied biology, biology just applied chemistry, which is applied physics, and so on. So we could all try to reduce to a very small set of rules or laws and describe everything. And then we know that nowadays, at least for practical purpose, this is nonsense. So every level of complexity or scale, there are new properties, emergent properties. And these new emergent properties has its own laws, which are somewhat universal, meaning that the the individual laws, the laws of the individuals that gave rise to these new phenomena, you can tweak it a little bit, but nothing will change to the emergent property. It is still there and they will be the same, even if you tweak the high energy laws of physics. Here this slide is just examples of these emergent complexity. You could put life here or mind if you want, many complex things that we do not understand. There's everything here, but I'll just talk a little bit about this one here, which is a termite hive. So this is a line north-south, so it optimizes the heat of the sun that is there. So the termites know that they have to build up in that way. Underground is a huge structure, so huge that makes our city like something of a playground for kids. There are chambers for food, chambers for reproduction, and all of this stuff, all well separated according to optimize survival. And I inquire who is the engineer of this city. Do they have a consciousness that they did that? How does it emerge? So this is an emergent phenomena. Here you have these, whatever material is that's a pyrochlore, and it turns out that the electron is not an eigenstate of this universe. You can think the pyrochlore is a new universe. The electron is not an eigenstate of that, and it fractionalizes itself. And it turns out that you end up with magnetic monopoles as the fundamental excitations of this material, and many others. Okay, so this is my final slide for contributions of condensed matter to other fields of physics, or we just say that we like to call it, this is cosmology, this is condensed matter physics, but when you go and think deeply on this, actually you are doing physics, and the nature doesn't care if you call it this and that. So you're describing nature, and nature is a unity. So these ideas of spontaneous symmetry breaking and normalization group, the ideas that I'm going to talk here, it permeates the whole physics. It's there in high energy physics, particle physics, you have a grand unification theory, so on, talking about phase transitions, the fields of the matter. You have Anderson-Higgs mechanisms endowing matter, endowing mass to the matter fields, and also endowing a gap to plasmonic excitations. It's the same thing. Fractional statistics, I just told you an example of the monopoles before. So these are all concepts that permeate many other fields of research and of our endeavor in understanding the universe. And the godfathers of today are these four: Landau, Wilson, Fisher, and Kadanoff. Okay, now phase transitions. What do I have to tell you? The basic concept is, what's a phase transition? It is, nowadays we classify in the simpler way as a non-analyticity of the free energy. So you have a partition function that has sum of exponentials, all analytic functions, so how you can have a non-analyticity. The culprit is the thermodynamic limit. Then you are summing infinite, and since you are summing infinite, then you can have some non-analyticity. There is a beautiful theory for putting these in firm mathematical grounds, that are the theory of Yang-Lee zeros, or nowadays Yang-Lee Fisher zeros of the partition function. So Z has zeros at the complex plane. Which complex plane I'm talking here? Now you get the temperature here, but you could say that the temperature has a real part and an imaginary part. In our words, we know that temperature has only the real part. So the real X is the real universe. Mathematically, these zeros are there, but they usually assemble themselves in lines, and they may touch the real-time axis in the thermodynamic limit. And in the thermodynamic limit, if you have a zero at the real-time axis, well, the free energy is a log of T minus Tj. Tj is these zeros here that I'm plotting in blue. So you have a log of 0, and that's your non-analyticity. We classify phase transitions in first order or continuous phase transition. A first order phase transition usually involves latent heat, which is good for us. Otherwise, when you are heating up the water for your tea, if there was no latent heat, when it rises at 100 centigrades, all that water becomes vapor and you get an explosion, because that vapor occupies a huge volume. But luckily there is latent heat, so it evaporates slowly. But if you go to this point in the phase diagram, there is a critical state, which doesn't happen in our everyday life pressure. And then this critical state, the difference between the liquid and the vapor vanish. They are the same thing. And there is no latent heat anymore. And the transition undergoing from the liquid to the vapor through this point is called a continuous phase transition. There is no latent heat. But there is something very special about that you have a scaling variance. The system looks like the same average length scale that you probe it. And this is nice, because then you can do field theoretical methods to describe the matter. And field theoretical methods are a well-established mathematical tool that physicists like very much. So still on continuous phase transition, this picture down here is a snapshot of the microscopic state of this critical property. We can say that black is vapor and white is liquid. And these keep fluctuating in time. This is just a snapshot. But you see fluctuations of vapor and liquid in every scale. There are fluctuations of this big size, there are fluctuations of that small size, there are fluctuations of even smaller size, and so on. This is like a fractal. So the fluctuations are of unbounded length scales. So it couples to the electromagnetic field, and it scatters light. So that's why it is whitish. So that's called critical opalescence. Because the modes of the system in this case has length scales as large as the wavelength of light. And what I want to tell you is that there is a description of these length scales, psi, as you approach the critical temperature. So away from the critical temperature, these fluctuations are not scaling variant. They have a size. And as you approach, the size diverges as this law here. T over minus Tc to the power nu, and this in the denominator. So psi diverges. But the time of fluctuations also diverges. And this is described by this other critical exponent z. It's called dynamical critical exponent. And you can compute other observables like other parameter, the difference between solid, liquid, and vapor, or in a magnetic transition would be the magnetization, specific heat, compressibility, and so on. So all these thermodynamic quantities have singularities at the transition. They are divergent if these numbers are positive. And the magnetization is finite for T less than Tc and 0 for T above Tc. So there are non-analyticities in the thermodynamic quantities And these non-ellasticities are described by this set of laws here that are governed by these critical exponents. And the nice thing about these critical exponents is that they describe the singularity of the matter, but they do not depend on details of the matter. So nu, beta, alpha, these called critical exponents, do not depend on the type of liquid, if it's glycerin or if it's water or any other liquid that you like. They have the same exponents. So this is what we call universality. So with a simple theory, I could describe these thermodynamic singularities of many different objects or liquids, for instance. So simple models can be used. And that's what physicists like, to simplify the problem, simple models. These same concepts apply for quantum phase transition. What's a quantum phase transition? Well, here is this lithium fluoride. It is a ferromagnet at low temperatures and a paramagnet at higher temperatures. And if you apply a transverse field to this compound, this transition temperature from paramagnet to ferromagnet decrease. And at some point, if you apply a very, very large magnetic field, you don't have the ferromagnetic anymore. So this transition happens at t equals 0 and is driven by the transverse field. So that's what we call quantum phase transition, and there is a quantum critical point. And the theory for this quantum critical point, you can also use field theories for that. You just need to apply one to say that there is an imaginary time dimension here. Don't worry about that. But there is a simple model for this transition, which is the Ising model. I'll talk about it more in a moment. Okay, so far for introducing whatever condensed matter physics is, people were very happy along the 60s and 70s. Many progress were done. But then there are these other dirty guys that comes and said, look, your sample is not that clean. It's not a crystal. There are defects on this crystal. And then the experimenter said, oh, my crystal is perfect. No, no, no. No crystal is perfect. There's always impurities. No, no, I have a clean room. No impurities in my sample. Yeah, you wish. Actually, the Nobel Prize of this year or last year of medicine was about that, because this guy looked at DNA of the Neanderthals. It was plagued with human DNA, nowadays DNA. And he has to go through a lot of breakthroughs to remove all the dirty and get the pristine Neanderthal DNA that was in the caves somewhere in Siberia, I suppose. Okay, so let's put disorder. Well, disorder looks, have this model here. Sigma IZ, sigma JZ, these are spin health variables. So there's a minus sign here, means that spin I and J wants to be parallel in Z direction or minus Z direction, whatever, they want to be parallel. Then you minimize the energy, right? If they are anti-parallel, this product here is -1, if a minus sign is a +1, it enhances energy, we don't like it. But the coupling energy, this J, may be site dependent. Maybe two spins here interact different than the two other spins there. In your sample, there are maybe vacancies. Instead of putting a magnetic ion in that site, you put a non-magnetic ion because there was impurity. And this is modeled by this epsilon here. Epsilon can be 0 or 1 with certain probability. The probability is the concentration of non-magnetic impurities. You can put the external field outside, as we seen here. And you can put a longitudinal field if you wish. Maybe your sample has more symmetry. So instead of having interaction only in the Z direction, it can have interaction in the Z, X, and Y direction. That's the Heisenberg model. But also the Heisenberg model can have your impurities and so on. So you can say, well, this is dirty physics. Now, how do I feel, right? The dirty physics guy are calling me dirty. So I'm the dirty of the dirty. And this should be a joke, and you're supposed to be laughing. Okay, now you're laughing. So I'm the dirty of the dirty, putting dirty in the dirty physics. And these are, you can say, oh, for phase transition, doesn't matter. It's microscopic details, we don't care about it. There is long wavelengths. You see, we have the field theory. This order will be averaged out and so on. Yeah, that's a wishful thing. So let's go to the experiments. And the experiments were done in specific heat. I don't know if you can see it, but in the x direction, the x in the vertical axis is log of specific heat. And in the horizontal one is the distance from the critical point, 1 minus T over Tc. And according to the theory, there should be a divergence at T equal Tc, but the experiments are not seen. So these lines here are not theory. These lines were plotted by experimentalists. So they didn't put the dots. These other experimentalists put the dots, but I'm not seeing any divergence there. So you see, you can say, wow, experimentalists can come to you and say, theorist, you don't know how to compute physics. There is no divergence. And you say there is divergence. There is no. I said, oh, no, wait a second. Am I a good theorist? And I say, it's disorder that is the culprit. Your sample is disorder. And the next experiment says, what? I'm a good guy. So, okay. So actually what has to do, we have to understand the effects of disorder in that. Maybe it's relevant or not. Or maybe it's another model. But being another model, it's not so easy to change the model, you see? We are talking about critical phenomena, and very few details are important. That's what we call about universality. So change the model, if it is, you do not change much, there is nothing going to change in the singularity of the thermodynamic properties or the critical exponents. They will be the same. Diverge is diverge, doesn't matter the liquid, right? But here some things happening. Then comes the guys in the late 70s, these two guys, Griffiths and McCoy. Griffiths in the left, McCoy in the right. And they don't ask me, but it is rigorous result. So these papers look at the titles. Non-analytic behavior above the critical point in a random Ising ferromagnet. So non-analytic behavior above the critical point, but the critical point is the one that has non-analyticity. So you have above it as well? What's going on? And look what McCoy wrote. Incompleteness of a critical exponent description for ferromagnetic system containing random impurities. What? I have all this beautiful theory that people are building by decades, and now it says that it's incomplete. And these are rigorous results. So there is no approximation here. This guy did real mathematical. God, this is very painful to read the paper. But they did it. So what's going on? So let's go back to our toy model, the transverse field, the Ising model. So that's the Ising interaction, this is the transverse field. And you should have something like that. If the epsilon is the dilution. So you see that there are vacancies here. It's because there are no magnetic ions there. So the black dots are magnetic ions. So there is your crystal. This crystal is there. It's not a defect on the crystal. It's just I'm not drawing the non-magnetic impurities because, well, they are non-magnetic, so they will not do anything for magnetism. So when there is no dilution, no impurity, then you expect some curve like that. Magnetization is a function of temperature. There is a critical temperature, and that's it. That's the clean theory. Everybody's happy with that. And here is the zeros, the Young-Lee-Fisher zeros. Now if you put impurities, now you put these vacancies here. What do you expect? Well, there are less magnetic moments. So the magnetization should be lower. right? There is less people to align parallel, and so the magnetic field should be smaller. And the critical temperature is the same. It also should be less because there are less interactions. So phase transition is competition between interactions and some fluctuations. In this case here, thermal fluctuations. So there are less interaction. I need less thermal energy to melt the crystal, the magnetic crystal. So I need less temperature here. So what Griffith was saying, lunarate behave above the critical point. The true critical point is this one here of your dirty sample if P is greater than 0. So above this temperature, there were no nonaticities. So he's saying there are lots of Young-Lee Fisher zeros here. And that's what he showed. There are many Young-Lee Fisher zeros there. Well, that's the result. So remember, and therefore, look what's going on here. There's log of T minus Tj. Tj is these red dots. So you should have a non-analytic behavior in this entire window of temperature. Wow, that's crazy, right? So people are saying, well, this will smear the transition by disorder. And the smear is a word that they were using in the 60s or 70s, which you read the papers and you do not find a definition of what's smeared. Maybe they thought that incompleteness of whatever critical exponents description is smearing. That's the definition of smearing. Or maybe it's because there are lots of non-elasticities here, and this is smearing. So you go from the paramagnet to the ferromagnet through a region that the non-elasticity is smeared over a temperature window, so something like that. So there was no clear concept of smearing at that time. So far it's rigorous mathematical, but do we understand what is really going on? Why those zeros are there? So one of the first to try to understand or quantify these singularities are those guys here, Anderia, Setna Palmer, Bray, and Thiel and Hughes. Well, it starts in the early 80s. Lots of time to understand, all the 70s. And Handeria, well, that's the first culprit, Indian culprit in the game. So he thought of the following. Let's go for t equals 0, for instance, right? At the quantum critical point. So the transition is driven by the field, not temperature anymore. But you still have the same type of physics. Why this guy drives the transition? Remember, if h is very large, we want to favor this operator, sigma x. But what sigma x does in an eigenstate of sigma z? It flips, right? So if you think that you are in a ferromagnetic state and you apply this operator, it flips the ferromagnetic state to the other one and keeps flipping. So this is what we call quantum, the source of the quantum fluctuations, because this operator does not commute with that one. It's just another competition. Now it's not thermal fluctuations, it's quantum fluctuations. 0-point energy, Heisenberg principle, you name it. So what this guy thought? Desperate times needs desperate measures. He thought like that. Look, there is this patch, which he calls rare region, which there is no impurity here. And this patch is large, okay? If it's large, and we are looking just a little bit above or at that window of temperature or window of fields, if the sample would be pristine, I would be in a ferromagnetic state. So locally, this patch is in the ferromagnetic state. So if it is ferromagnetic state, what are the eigenstates? So if you look at the local spectra of this red region, it's either everybody up or everybody down for zero field. But if you turn on the field, we know this will split. And there will be a tiny split between this up and down. And this tiny split is exponentially small in the volume of the red region. And you can work that out by perturbation theory. Just because you are going to the system once it's pristine, it wants to be ferromagnet, it wants to become classical. Forget about the quantum fluctuations, but then you turn on quantum fluctuations. It is finite, it cannot be classical, it cannot go to a true phase transition because true phase transition only happens in the thermodynamic limit. The rare region is not in the thermodynamic limit. It's almost there. So that's why you get this exponentially small splitting. Meaning what? That this rare region will be fluctuating up and down very slowly. Time is energy is inverse of time. So if you prepare the system, this rare region, the up state, it will take an exponentially large time to fluctuate. So these rare regions are very slow. If they are very slow, they are highly susceptible. If you apply a magnetic field, it will align with this magnetic field. To fluctuate down, forget it. It will take lots of time, exponentially large time. So if you want to compute the density of states of that, it's very simple. You sum over all possible rare regions in its volume. What is the probability of finding a rare region? It's exponentially small because you need no impurities there. So you need to flip the coin and always have heads. No impurity, no impurity. This happens exponentially rarely, right? So you put an exponential here. And then you say, why do I care with something that's exponentially rare? Because this thing that's exponentially rare has exponentially large response. It tunnels exponentially slow, which gives exponentially large response. So now you have this delta R. If you want to excite the state, for instance, I want to give some energy for this system. If this energy is tinily small, it will be absorbed by the rare region, going from this state to the other state. So you weight one exponential to another exponential, two exponential, compete with each other, and you get a power law. Meaning that the density of state due to the region diverges as frequency goes to 0. What does that mean? It means that there is no gap. But the bulk is gapped. The bulk is paramagnetic, so everybody's aligned to the field. If you want to excite a state, you have to flip against the field. It pays energy. So the bulk is gapped. So all the thermodynamics, the low energy thermodynamics, will be dominated by these rare regions. Wow, how come? Something that's exponentially rare, you don't care about it, will dominate the thermodynamics. And that's what this guy showed. So that's why you have these many zero here of the partition function. They are due to each rare region. The rare region is putting zeros here because they are almost ferromagnetic, but they are not. So nowadays, we know that this is the phase diagram. You have a quantum critical point, and surrounding this quantum critical point, there is this Griffiths ferromagnet and Griffiths paramagnetic phase, which are gapless. So this blue curve here is the spectral gap. In the clean system, the spectral gap vanishes only at the critical point. It's gapped at the ferromagnetic and in the paramagnetic phase. So what I want to say is that now you have gapless excitations and finite correlation length because these rare regions are finite. How can you have finite correlations, gapless excitations without Goldstone modes? Whatever it is, right? Now I'm talking to my colleagues that know what that means. So so far, that's what I want to tell you. So the question is this general? This is mirroring of the transition, like having these strong singularities will always happen. The critical behavior will be always destabilized by disorder. And then comes Mr. Harris, and he thought of a simple way to compute it. So he get a sample, break the sample in hypercubes of size correlation length, which is the length scale of the problem, and assign to each hypercube its distance from criticality. So, and then compute a histogram. So that's the histogram here. If R is large, means that it's very distant from criticality. This may happen if there are lots of impurities there. If this other hypercube has a small distance from criticality, means that maybe this is due to a rare region. It is willing to go to the other phase more rapidly than the other regions. So you have this distribution of a distance from criticalities, right? You have an average and you have a width. How do you compare the average and the width when you lower the temperature and it goes to the transition? So this R is T over Tc of the block minus 1. So the transition happens at 0. So here I'm this other phase, the paramagnetic phase. Now I low temperature, and what happens to the distribution? Does it broadens or does it sharpens? Sharpen. Well, the width of distribution, he thought. When I go to the transition, remember, this length scale diverges. That's what happens, right? A critical point. What happens to this width? This width has to go to 0 because when I increase the hypercube, I'm averaging, now let's say that I double this hypercube. So now the R of these 4 here is R1 plus R2 plus R4 plus whatever, R5 divided by 4. And now I'm doing an average. We know by the central limit theorem that this width has to goes to 0 as square root of the volume. So the volume psi to d, and the square root is the 2 here. So now the average of the distance from criticality. Well, the average of the distance from criticality, you relate to the volume of the hypercube by the definition of the correlation function exponent. It's this number here that I was telling you before. So you compare both, and you arrive at this very simple equation. We tell you that the following: if d nu greater than 2, this exponent is positive, and when psi goes to infinite, this goes to 0, means that it sharpens. So the clean critical behavior should be stable, in the sense that if I want the clean theory to be consistent with disorder, well, the clean theory says what? The clean theory says that everybody goes to the transition at the same point. There is only one critical point. But if the distribution broadens, this inequality is violated, then you expect disorder to be relevant. So that's the criterion by Harris and by this work. This criterion was in appendix of this paper. You go to his paper, his Journal of Physics in the 74. He wrote lots of things about the Ising disorder magnets. Everybody forgot about that. But the appendix is this slide. And he got the Larson Saga Prize in 2007 for that appendix. So never neglect your appendix. The appendix is a rare region in the paper, but the rare region can dominate things, right? See, the prize. And then you go to experiments. So in the experiments, you expect, for instance, the critical behavior of side diluted three-dimensional Ising magnet. Alpha is greater than 0. If alpha is greater than 0, means that this is violated. There is a hyperscale, there is a relation between these critical exponents, and these inequality translating alpha less than 0. So if alpha is positive, the Harris criterion is violated, so you expect this ought to be relevant. So that's the pure Ising computed by numerics. You don't see that in experiments. The experiment is alpha negative. So this is a new exponent that's not in the theory, in the clean theory, but is in the dirty theory. So far we have seen that off-critical Griffith singularities are due to its low rare regions, And we have seen stability criterion, which I did not talk about rare region in this criterion, right? I was just doing central limit theorem and average over distance from criticality. Where are rare regions there? So these two things are disconnected until 2014. So how things are evolving. And in 2014, these two gentlemen up here came up with the idea of marrying Griffiths, McCoy, and Harris. So now you have to do take a little bit of care with this distribution. This distribution in the middle is central limit theorem. In the tails, you have to be careful if the tail is not a Gaussian. So the central limit theory does not apply to the tails, it just applies to the middle of the distribution. So you took care of that. And we took care of the finite size scaling as well. So remember I was telling that you can compute this splitting via perturbation theory, but you can put finite size scaling there, whatever it is. It's a well-established theory. You can look at this paper here, for instance. And you can see that it's still exponentially small, but the rate, this number here, this volume of the rare region, let's say, it depends on its distance from criticality. So you now marrying what Harris was doing, applying the distance from criticality here, which now involves the new exponent and dimension, with the idea of slow rare regions, meaning that you have to do this integral. And after a tedious calculation, then you arrive in a new, actually, criterion, which recovers the Harris criterion if you are below the lower critical dimension, the upper critical dimension, doesn't matter what it is. But you really compute the singularities of these rare regions, and we recover Renderia results. But we can go further. We can actually classify all types of rare regions. We call it fast rare regions if the Tunneling rate is a power law with its volume. Slow rare region if the tunneling rate is exponentially slow with its volume. And we also call static rare regions if they do not tunnel anymore. And if you plug these three types of functional forms that we know of from mathematics, then you get the three types of singularities, and you can classify all types of singularities in phase transitions. I'm going fast here. I just want to tell you that these exist. And so this is the progress that we have been doing in this field. But so far, we did not talk about the critical point, right? I want to tell you about the critical point. And that's the dirtiest story. So to tell about the critical point, I have to go through these methods, strong disorder RG. And the culprits are, well, the original papers are by Dasgupta and Ma. Dasgupta is somewhere north in India. Bangalore, okay. And Ravin Bhatt and Patrick Lee. So those are the culprits. They invented this method. And this was good because, you see, it's an emergent phenomenon. Something that I didn't tell you about emergent phenomena is that it arises unexpectedly, meaning that the phenomena you cannot predict just looking at the individual parts. So what are the individual parts here? China and India, so they are collaborating. Nowadays, I don't think that's happening anymore. But okay, new beautiful things appear when you put things to interacting together, right? Okay. I hope you do not get offended by this joke. So okay, they invented the method, but they did not solve the equations. And I will show you in a few minutes the equation, how nasty they are. The guy who solved the equation was Daniel Fisher, and for that he got the Lason Saga Prize. So I don't know if it's unfair with these other guys here, but I don't know. So he solved it, and he pinpoint the concept of infinite randomness that I want to tell you here in the last few minutes. So that's the random transverse field using chain, our toy model. The Harris criteria says this order is relevant because the critical point of the clean theory is 1, D is 1, so this is violated, so this order is relevant. So if you try to solve this problem using few theoretical methods, the usual theoretical, you fail miserably. It's unbelievable how wrong you could not be even more wrong. So you have to do the methods or the strong RG that Madhas Gupta, Bhatt, and Lee have invented. And this method is so powerful in the sense that it doesn't take any average about disorder. It works the length and the energy scale locally. So I will not do any average. I will just look at the so many energy scales that are in the problem. This sounds very complicated, right? But there is a key fact that makes all things simple. The method uses disorder to its advantage. It says that let's suppose that disorder is very strong, meaning that this energy scale, these J's and H's here, they are distributed through large length energy scale. The smallest one is millikelvin, the largest one is 10,000 Kelvin, something like that. Let's just assume it. And if you assume that, the problem becomes much easier. So what they do? Well, they do, as just I said, search for the strongest bond, let's say H2. H2, 10,000 Kelvin. And these J's here, I don't know, a Kelvin. So I do perturbation theory. This spin will be mostly aligned to the field. And to counter-align it, I pay lots of energy and I look at low temperatures. I want millikelvin physics. So I don't care, or ground state physics. So I don't care about this high energy state. I throw it away. So if you throw this spin away, you break the chain too, but you have to connect the chain. Of course, if you break the chains, you're doing a very crude approximation. So if you do perturbation theory, you connect the two halves of the chain by this new coupling, which is Jj over H2. H2 is omega, which is the maximum of all the energy scales in the problem. But maybe it turned out that the coupling is very strong. Again, these, I don't know, 100 kelvins, and you're looking for 1 Kelvin, and these local fields are millikelvin. So forget about these fields. These two spins, they want to be always aligned, because you have a ferromagnetic state, up, and down, down. So whatever they do, they will be together. So you have only these two states. Forget about these other states up here. They are not excited. So two states, it's a spin half, right? It's a single spin. They are together, so if you know one, you know the other. So this is a cross-graining. So I get these two spins and put as a single effective moment there. And of course, this guy will not be either in the up or in the down. It will start fluctuating. And start fluctuating because there are these H's here. But the effective H is HH over J. It's more or less what we have here, exchange J by H. This comes from duality. So now you go to the dirtiest of the dirty. So here is your chain. So you look for the strongest coupling, is this, let's say, is this interaction, and then you fuse it, and you put them here. So here in this line will be our ground state, and on the top is the normalized chain or the coarse grain chain, if you wish. Now you keep doing this. Keep doing this. Now you decimate a field. And now you decimate a coupling, and decimate a field again, and a field again, and a field again, and another field, another field. Oh, now it's a coupling. Now another coupling. Then you build up your ground state. So the ground state is what? This one here, they are aligned with the field. So they are in the paramagnetic, locally paramagnetic, up, down, down. But so are these blobs here. But they go up, down together. This guy and this guy, they are up, down individually. But these ones in the circle, they are up, down collectively. So very slowly. So very slow, very low energy. So if I want to excite this state, I will, the lowest energy will be taken by this guy collectively going up and down, up and down. So these are localized modes, but they are extended. So do not think that localization, delocalization, or delocalized modes means extended modes. They are not synonym. Extended modes are modes that does not have a length scale. Delocalized modes is modes that travel throughout the system. The mode does not travel throughout the system, so it is localized, but its length scale is not finite. It can cross the entire chain. So this is new physics happening in this model. So you can work out the flow diagrams. I will not go through many detail because I only have 5 more minutes. I will show you the flow, the equations that you have to solve to take care of this renormalization of the distribution. Remember what we are doing here in this RG. I'm not taking any average. I'm just renormalizing couplings because every time I do one step, I remove the J's that were original J's and insert a new J that is J over omega. So these distributions of couplings and fields, they are changing as I access the low energy. And these are the equations. So you see, it's very nasty equations. It's integral differential couple equations. You could not do worse, right? But Daniel Fishers could solve it. And that's the thing. He solved for the critical point. And look what he found. He found that doesn't matter the distributions that we start, you always flow to the same fixed point distribution. That's amazing. And the distribution has a huge singularity at 0, right? Because you are doing this J over J, perturbation theory, building up lots of zero energy excitations. And the thing is, it's universal fixed point distribution. Doesn't matter how weak this order is or how broad it is, you always flow to this fixed point distribution. So all these other systems, doesn't matter the details, if I want to describe the low energy physics, I just have to think that the energy scales are distributed according to this function, which is a power law. But it's a power law, very peculiar power law. The thing is of infinite randomness is the following. If I get this functional form here of this distribution and compute its width, the second moment, and divide by its average, it diverges as you lower energy. Meaning that these energy scales are broadly distributed. The disorder is infinite. The width is much, much, much greater than the average. So you cannot do any average. If you want to describe this state of matter, forget about average. It's broadly distributed, the energy scales. So arithmetic average and is not a representative of the many energy scales. You have to take care of all these energy scales. And this is 1D. You can build up, I showed you how you do that. In 2D you do this. And when I look at that, this reminded me that artistic representation would be something like this by Pollock. So, you know, we are sophisticated guys also. We want art. So that's the phase diagram that we have built so far. This is the clean case. When you put disorder, you end up with these Griffiths phase surrounded that are gapless. And in the clean theory, you should find the magnetization with this critical exponent. In the dirty theory, is a different exponent. You can compute the dynamics of this state. For instance, if you look at this correlated cluster and prepare it in up state, it will relax to the down state, and up state you keep tunneling. And if this cluster has size L, what is the typical time that it needs to relax, and that's the relation between the time and length scale. It's very different from the clean system. In the clean system, you have the time and length scale are power law related, and in this case, this critical dynamic exponent is equal 1 for the clean system. But you don't have power law, you have exponentials in the dirty system. So the log of t goes with exponential of L. If you exponentiate that, then you get exponentially large time. This exponentially large time is, you can understand in the following sense. Remember when you do the renormalization, is Jj over energy. So energy renormalized multiplicatively, but the size of this blob is additive. You just sum the distance. So energy multiplicative, energy space additive. So that's why you have a log here. And this exponent psi is universal. Doesn't depend on the matter of the details of this order, is 1/2, and it's just because 1/2 is a random walk. So you are multiplying energy divided by energy. So you are some energy divided by log energy, let's say in the log scale. So that's why you get the square root. So it's random walking energy scales. So it's unbounded, and that's why you get all these strange things. You can compute all the thermodynamics, so see how different the random from the clean system. I will not tell you, of course, how it happens, but there are two universal exponents. This psi that comes from the random walk, and another exponent that the golden mean. So how the golden mean can appear from there? There is a funny geometry of these clusters that I do not have time to explain that, but there is a beauty on that. You know the golden mean is a ratio that is related to the beauty of all these arts, paintings, and so on. You can compute correlation functions. The correlation functions are very odd. If you compute the average correlation function, it's dominated by the spins in that cluster. So the correlation function with the distance vanishes algebraically. But typically, two spins are not in the same cluster. So they have a very weak correlation. So typically, the correlations vanishes exponentially. So mean correlation functions, typical correlation functions are very different. So that's why you cannot replace everything by some average. You can compute the offered critical thing of critical properties, but I'm not going through that. So far I was telling about the random transverse field is in chain, but this physics happens in many other systems. Transverse field is in chain, I just told you. It happens in the Ashkin-Teller model, in the Potts model, Clock's models in any dimension. So I put just some papers. It's not at all exhaustive. The literature is huge, but I put some Indian culprits here, Senthil, Majumdar, Narayana, that is sitting right here. This also happens in SON, SUN, SPN, symmetric, and anionic spin chain, so very exotic physics here. Emergent symmetries appearing. There is description that in the SU3 that is just like description of quarks in chromodynamics, but I will not tell you about that. It's very beautiful. Superconductor metal transitions in itinerant and itinerant ferromagnets. All these physics in that phase transitions as well, between a superconductor metal and between an antiferromagnetic metal and insulator, a paramagnetic metal. So culprits, there are other Indians here, and there's been, these two papers are experiments. We try very hard to publish a PRB, and the experimentalists that just confirm our theory goes to science. And more recently, there have been collaboration in India that have shown that as well in other superconducting heterostructures samples. So. Non-equilibrium phase transition reaction diffusion models that model epidemic spread, something that's very fashionable nowadays. You find this type of physics there. random walks in random media, of course, random, right? Of course, there will be the Dirtiest Physics there, even flow criticality. So, okay, conclusions. Show you that there are gapless Griffiths phase that generally surround the critical point, and this Griffiths phase is plagued by singularities due to its low rare regions. Rare regions what? This large patch, which is in the wrong side of the phase diagram, locally in the wrong side of the phase diagram. So they are very slow. And with that, we can classify the Griffith singularities according to their dynamics, if it is exponentially slow or power law is low. And we can come up with a stability criterion marrying Harris criterion with Griffith singularities. And I showed you this strong disorder G, which is a new tool for when our field theoretical methods fail, just because the physics is different. More is different. And you get this infinite criticality, which is in the title of this talk. So you have this localized and extended low energy excitations. Localized and extended are not how do you say? It's not an absurd, not contradictory. You have an effective disorder that in the infrared limit diverge. And average and typical values of observables behave quite differently. Many collaborators to think about this topic of infinite randomness. Raj is here, sitting there. Thomas Voita in Missouri, Nicolas Lafranci in France, Toulouse, Adrien de Maestro in Vermont, or I think he's there. André Vieira in São Paulo. Wada, Quito, Getelina, former students and postdoc, my former advisor, and Xavier, which is in a nice state in Brazil where the food is very nice. And he's been helping me with the MRG calculations. And I thank all these collaborators for playing with me in the mud. And to end, I answer Mr. Pauli objection of solid state physics is dirt physics and one shouldn't allow it, and I think I beg to differ. It's a lot of fun. Thanks for your attention.
Thank you very much for your wonderful and entertaining talk. Now it's time for questions.
I have a couple of questions. You have these nice decimation diagrams, which does that help solve those equations? I mean, that looks like some real space kind of RG.
Yeah, it is.
Does it help solve that equation?
These equations are mathematical description of that RG, precisely that.
Okay.
So there is no approximation in writing these equations and with respect to the decimation that I was doing here. It's exactly the mathematical description of this thing here are these flow equations. It is true that you can think that these are real space RG, but I would say that it is actually an energy-based RG. I'm looking at the energy scales. I can do it locally because the modes are localized, but what is the real fundamental philosophy behind is the energy-based RG.
And these are quantum or the classical field?
It's in this case, for these ones, the quantum is in model, but as I was telling you, this also applies for non-equilibrium reaction diffusion models, which are classical models. So as long as you have some sort of fluctuation and interaction, you can try to do this sort of approach.
One last question: can you solve the quantum 2D quantum energy model with strong disorder? Because without disorder we don't have it.
Yeah, I put the 2D version here. The 1D you can solve analytically.
Yeah, I'm asking.
In 2D, the connectivity of the lattice mess up, and you cannot solve analytically, but you can implement this procedure in the computer.
Yeah.
And you can go to very large system size, and everything agrees with that. So far, infinite randomness, as I was flashing very fastly here, it happens in these models in any dimension, even infinite dimension. And this, we have a analytical understanding of that based on the rare regions.
Thank you.
Next, please. Okay, if there are no further questions, let's thank the speaker once again.
Thank you for your attention.
Now I request Professor Rajesh Narayan to hand over a moment to Professor José from our department.
Thanks a lot, Raj.
Thank you so much. Now you'll have to pack that in.
Thank you, and thank